Hello, I'm here to talk about a bellwether of aircraft design because for over 100 years, we've been using the same lift distribution that we believe to be the most efficient for all configurations. But there's now computational evidence to the contrary. So the original inspiration for flight was birds. They've been optimized for flight for over a thousand years. They have a simple design, and they're able to fly and coordinate turns without the use of an observable yaw device. So in 2016, Dr. Bowers and his research team at NASA, they uncovered some of the early works of Ludwig Prandtl and his revision to this elliptical lift distribution in 1933. So they uncovered the bell-shaped lift distribution, which Ludwig Prandtl says is best for other aircraft configurations, namely a flying wing. So Dr. Bowers was able to prove minimal induced drag and the production of proverse yaw as a consequence of using this new lift distribution. Um, that is to say, whenever it rolls into a turn, it also has a yaw motion into that turn as well, whereas the elliptical lift distribution in aircraft we see today have the natural consequence of adverse yaw when performing a turn, because the high lift wing is going to produce more induced drag due to that higher lift being produced. So the inspiration for the aerodynamic design of this aircraft is birds. So we looked at the albatross and we looked at that airfoil cross section of their wing, and we wanted to closely mimic that, not only in the airfoil cross section, but in the fuselage profile, in the wing plan form, and in the overall aircraft shape. We wanted to introduce some avian biomimetics as a part of this aerodynamic design. So this effort is largely computational by use of computational fluid dynamics in star CCM+. So this effort involves matching 4 different lift distributions in CFD and evaluating their aerodynamic performances, being lift to drag ratio and other performance in level steady flight, as well as in a bank turn in evaluating proverse yaw of these different lift distributions. So the one shown in orange is a modern bell curve. The one shown in white is a cosine curve. The one in blue is Ludwig Prandtl's revised curve, the Prandtl bell curve. And the one in green is Ludwig Prandtl's original curve that is supposed to be the most efficient for all aircraft, according to the findings in 1919. So the one in green is the one that is still currently used today, and that's going to be put up against the Prandtl bell curve for this flying wing configuration. And the CFD shows that the Prandtl bell curve has the highest lift to drag ratio in a level steady flight type of analysis, and the elliptical actually performed the worst. And this is going to show the drag distribution from wingtip to wingtip of the aircraft. Just noticing that for the aircraft configurations that are producing more lift towards the center, they're also producing more drag towards the center, and contrasting that with the bar graph on the right that is showing that the more centralized the lift is, the more proverse yaw into the turn they're going to have. But you can see the Prandtl bell curve is the one that coordinates the turn the most, in that it does not have a whole lot of yaw force when rolling. And this is largely due to the upwash that is happening. When the lift is more centralized, there's a region of upwash that happens at the wingtips of the aircraft, as opposed to the elliptical lift distribution that is creating a noticeable amount of lift from wingtip to wingtip, and then you get a sharp region of upwash that is outside of the aircraft wingspan. So from this, Dr. Bowers and others have observed that birds may be using this same bell-shaped lift distribution. This is observed by their spacing and their wing overlap in a V formation. So we believe that they're using the entire region of inboard upwash from the bird that's flying in front of them. So we can use that region of overlap to determine that that is likely the point at which the upwash is occurring. And that appears to be congruent with what we see with the Prandtl distribution in the figure above, where we get this inboard region of upwash that is happening at 70.4% of the span. And the CFD results show the same thing as observed by trailing vortices here. So the figure on the left shows the elliptical lift distribution. And what you're seeing is that at that very wingtip, you're seeing the strongest vortice, and you're seeing that sharp region of upwash that is indicative of the region outside of that strongest vector indicated in red. And on the right, we have the Bellwether lift distribution, which is going to be not as sharp. You see the vectors are a little bit more smooth. There's a little bit less of a gradient. And that strongest vector is 70.4% of the span, according to the measurement tool in STAR CCM Plus, which is almost exactly spot on and congruent with the findings of Dr. Bowers and the research team at NASA. So the future of the Bellwether aircraft, it still needs to be fabricated, and it is going to seek to use leading edge sensing to experimentally gather angle of attack data along the wing to help generate what we believe to be seeing the lift distribution in flight. And so we're hoping to match that lift distribution measured in flight with the lift distribution that was developed through the computational fluid dynamics. Additionally, we would like to understand the benefit of the roll-yaw coupling by extracting the inertial measurement unit data and seeing how much yaw is produced in a rolling motion. So this is revolutionizing the way we design flying wing aircraft, seeing that it is not only more efficient aerodynamically in steady level flight in producing a higher lift to drag ratio and being more efficient, getting more range and endurance, but it can also coordinate a turn like a bird without an observable yaw device. Thank you.